bang bang or pat pat right hand rule. Before we discuss this, we want to review briefly that this symbol here means out of the page, and when we have an X, that means that some quantity has a direction into the page. And the way we can kind of remember that is if we think of an arrow that has a conical tip. So there's the arrow, and here are the feathers in the back. If this arrow is coming towards us, if it's coming directly towards us, then it looks like what's in the upper left corner. It's coming out of the page at us. We can see the tip of the arrow, and then we can see the conical portion at the bottom of the arrowhead. If it's going away from us, then what we'll see is pretty much what's in the upper right here. We'll see those feathers, and then we'll also see the bottom of the conical arrowhead. That might be a way you can remember that a dot means out of the page and an X means into the page. We're going to go through here the right and left hand rules for the magnetic force that is on a moving charge. And this is a very important word right there, on a moving charge. In an earlier video, we discussed the Thumbkin-Twiston right-hand rule, which is related to the direction of a magnetic field that is created by a moving charge. And now we're talking about the force that is on a moving charge when it is moving through an external magnetic field, somebody else's magnetic field, we might say. The vector cross product equation for magnetic force that relates to these quantities is right there. What we have is a charge that is moving, and it's moving through an external magnetic field. This is not the magnetic field that the moving charge is creating. The moving charge is creating a magnetic field, but that is not this field. This is a charge that is moving through somebody else's magnetic field. A moving charge is not going to experience any force due to the magnetic field that it creates, but it will experience a force if it is moving in a particular orientation with regard to an external magnetic field. The way we can remember this is a couple of right-hand rules, which I've named the bang-bang right-hand rule and the pat-pat right-hand rule. And the bang-bang right-hand rule is called the bang-bang right-hand rule by me because it's kind of like bang-bang. You got your thumb, you got your pointer, and you got tall man all at 90 degrees relative to each other. And if you use your right hand, it looks like that. If you use your left hand, it looks like that. The way we do this is the thumb represents the velocity. For the right-hand rule, we use positive charges. This is similar to the Thumbkin-Twiston right-hand rule, which we talked about in an earlier video, that the thumb represents the direction of the velocity. The pointer finger represents the direction of the external magnetic field, and then tall man here points in the direction that the magnetic force will act on this moving charge. If we have a negative charge, Thumbkin points again in the direction that the charge is moving. We use the left-hand rule for negative charges. Once again, pointer finger represents the direction of the external magnetic field that this charge is moving through, and then tall man points in the direction of the magnetic force on, in this case, the negative charge. That's the bang-bang right-hand or left-hand rule with regard to what direction does a magnetic force act on a moving charge. Now, I actually prefer what I call the pat-pat right-hand rule. It is exactly the same, but I like the pat-pat right-hand rule for this reason. We use the right hand for positive charges, and the fingers here represent the external magnetic field. And this is why I like the pat-pat right-hand rule, because when the fingers are pointing out, that helps me remember, oh yeah, those are the field lines of this external field. And we call it the pat-pat right-hand rule because the direction of the force will be pat, pat. It's going to come out of the page towards us like that, like you are patting something. Let me back out this camera just for a second. So the pat-pat right-hand rule, if I have a positive charge moving towards the top of the screen and I have the magnetic field directed towards the left, then I'm going to pat, pat. See how you can pat something? That's why I call it the pat-pat right-hand rule. If our moving charge is negative, then we need to use the pat-pat left-hand rule. Once again, the fingers point in the direction of the magnetic field through which this charge is moving. And once again, pat, pat, but this time with our left hand. In this case, the way this diagram is oriented, the magnetic force is going to act, in this case, towards the camera. Our left hand, charge is moving towards the top of the screen, magnetic field is directed towards the right, and pat, towards the camera. Pat, pat, pat. That's why I call it the pat-pat right-hand rule. So let's practice here with just a couple of these. I have made a fairly lame copy of what's going on here. The nails represent the fingers, and then we've got RT, that's your right thumb, and then we would use this one here. That way I don't have to keep backing the camera out. Let's see what we've got here. Let's try this one on the lower left. We've got the positive charge, so we're going to use our right thumb, and the right thumb needs to point in the direction the charge is moving, and then our external magnetic field points up like that. Which way is the magnetic force going to act? You can see the little, looks like a bullseye here. It's going to be towards us. So FB, for this case, is going to be out of the page. For this next case, there's no magnetic force. And the reason there's no magnetic force is because in order to have magnetic force, look at the equation that we went through right at the beginning here. V and B, we're taking the cross product. And if you have two vectors that are parallel or anti-parallel to each other, the cross product is zero. This moving charge, if that's the external magnetic field, it will just cruise right on through there. It doesn't even know that anything is in the vicinity. It's just going to keep right on going. No magnetic force on that positive charge. How about the third case? We have a negative charge, so I need my left thumb pointing in the direction of the velocity, which you can see is towards us. The left thumb is going to be pointing towards us, and the field lines are pointing to the right. Perhaps I should do this just with my own hand here. All right, let me back this out. The magnetic field lines point to the right. The charge is moving towards us, so pat, down towards the bottom of the screen. FB is acting that way. And last, we have the right-hand rule, because we have a positive charge. Charge is moving towards the top of the page. The magnetic field is directed into the page. Get your right thumb out, point your fingers into the page, and which way do you pat? Whoop, to the left.